Hi everyone, and welcome to this week's lecture, or the first of two lectures this week. Today's lecture is on causality and experiments. So the plan for the day, we're going to first define causality in minimalist terms, and then discuss some challenges to causal inference when we use observational data. Then we'll talk about experiments, which are generally a better method for drawing causal conclusions. We'll talk about why they work. We'll talk about some threats to even the best experiments. Then we'll go over experiments in a little more detail. We'll use the work of Diva Pager, her 2003 study, which many of you have probably heard of before. We'll use that as an exemplar, and exemplars are kind of a term of art that we'll use in this class. It basically means a paper that, whether it's fully right or wrong, does a lot of things right, and we can learn from its mistakes in a way where the mistakes are the mistakes of, not even mistakes, but points of criticism where any reasonable person might have made that decision. You may choose to disagree with it. Sorry about that. But it's instructive to think about why they made that decision. Then we'll talk a little bit also about a famous natural experiment, which is Card and Kruger. And we'll talk a little bit at the end, I forgot to mention this, also about experiments that are done on a mass scale using digital techniques. So here's the general takeaway. Causality is hard to infer from observational data, where those are defined as data which the researcher does not directly intervene in. So it's a situation where we obtain the data set from someone else, or if we gather it ourselves, we in no way interacted with the subjects in a way that told them to do something or not do something, other than fill out the survey. There are some basic multivariate approaches, such as multiple regression, that allow us to control for some variable or set of variables, although this can be challenging. I'll discuss this a little bit later. So it's useful to think about when and how we can conduct experiments. They are harder, but they're more informative, and thinking about their merits helps us emulate them when we can't do them. Experiments can also happen outside of a laboratory setting, and sometimes we even encounter what are called natural experiments, which we'll want to discuss in some detail because they have a lot of advantages. On a practical note, there's no obligation to do experiments on your projects, but it is important for you to learn a little bit about this so that you're well informed about social science. So let's talk about causality. What's a working definition that we can all use, and why do we care? A causal effect is defined as follows: a change in some variable x, where x typically means a predictor, although in this case we're going to be more specific. It's something that we're saying is causal, so we know it's causal by definition, leads to a change in y, all other things being equal, or ceteris paribus, which is a Latin phrase that basically means all else equal. So what this means, it pretty much lends itself to an experimental definition, is that if you had two groups of people, or maybe just two people, who are identical in every way, but for the presence of x, and it doesn't have to be the presence or absence, it could just be a marginal quantity of x, meaning a change from where people are at currently, that's what it means to change at the margin, that marginal change in x will lead to some marginal change in y. So a running example that we'll use throughout this lecture: does the number of siblings that you have predict your score on a vocabulary test? If, and I should have written, actually, does it cause your score on a vocabulary test? We should actually probably fix that now. It's kind of important. So we have cause your score to increase or decrease. So what this would mean would be that if you were to consider a situation where we've either got a control group and an experimental group, or we simply happen to be able to observe in the population groups of people that are basically identical, but for certain levels of this variable number of siblings, does that, when you set aside those other variables, or more exactly you adjust for them, cause your score on a vocabulary test to increase or decrease? One way to think about it is that at that point, causality sort of becomes a philosophical thing. So we can get into, for instance, the difference between mechanical causality or final causality, aka teleological causality or formal causality. Those things we don't need to worry about here. For the sake of social science, there's kind of a famous working definition supplied, I think originally by John Stuart Mill, but adopted by Donald Rubin, among other people, is that basically if you have two groups of people that are fully identical, but for a marginal difference or an absolute difference in the presence of a variable, that's basically what we mean by causality. Whether or not we can identify a particular mechanism and those other things are sort of philosophical issues. So why do we care about causality? Well, first of all, human curiosity, right? We're partly here for the sake of intellectual enterprise as such, and it's interesting to understand how the world works. So does a large number of siblings actually cause lower scores? It's interesting, right? Policy interventions. So maybe possibly less pie in the sky. If having large numbers of children causes people to have worse scores, should we incentivize smaller families? It's kind of on some level an ethical debate in itself whether or not the state should incentivize any particular level of fertility. But assuming that most people would agree that some very minimal nudges, not any kind of requirement that you do or don't have a certain number of children, but things like, for instance, a tax credit or a family leave policy, things that certainly incentivize having children or not, then we may want to know, for instance, whether or not this is a possible downside of having more than a certain number of children. And not so much for the parents in this case, but for the individual children. So that would just be an example. So let's talk about why this is difficult to actually infer causality when you only have observational evidence. First, you could have reverse causality. So in our example, this is actually not a huge deal since most people's adult word scores on the GSS, where I'm gathering these data, almost certainly can't affect their number of siblings. You'd have to have some kind of crazy scenario where, you've got a very young adult, that's really the only way this would work biologically, who gets a terrible score on their, ACT, and mom and dad are like, all right, I guess we need to, have another kid because our first one is doing so poorly. I'm allowed to laugh at this as the oldest who would be the type of people to, suffer from that or be the scapegoat. But this is really obviously kind of a silly thing. It's very unlikely to happen. So that's not a problem here, but many such cases do exist. So for example, does your education level cause your spouse's, or is it vice versa? It's really hard to say, and in some scenarios, there really might just not be a very good answer. One thing I didn't put in the slides that's really worth noting is that, in general, statistical techniques are good at uncovering whether or not associations exist, and association simply means when people say things like correlation and they're not speaking very exactly, and they mean simply that two variables have a relationship statistically, that's basically what association is the proper term for. Correlation means a very specific type of relationship that I would encourage you to not use unless you mean that exact type of, basically a linear relationship between two quantitative variables. There's other kinds. So you might also have the problem of mutual determination. So X could cause Y and vice versa. This is the chicken and egg problem from philosophy. It's basically problem one on steroids. So again, this could also very clearly be happening with you and your education and your spouse's education, and indeed it almost certainly is. Finally, you could also have the problem of a spurious relationship, and maybe this is a bigger deal because it might be kind of quixotic to say that you cause your spouse's level of education or vice versa. Most people might think that that's kind of a stupid debate, to be honest, and I kind of tend to think the same because, first of all, you and your spouse, it really, like, one spouse versus the other spouse, those aren't coherent identities. Maybe we could say husbands and wives, assuming heterosexual relationships, but if we're just thinking about such an abstract case, such as you, the respondent, and your spouse, those aren't even really good sociological questions, to be honest. They're just things we happen to have data on. So in that scenario, there's really not much sense in that question. Spurious relationships are more interesting, but also more insidious because what's happening here, I'll explain this notation in a moment, but just hear me out on the description with words first, is that it appears that X causes Y, but once we account for some third variable Z, X does not cause Y, and this can lead to very problematic and false inferences. So what this notation means is that Y is independent of X. You can see that this is basically a pair of perpendicular lines, and indeed it actually turns out that, quite fascinatingly, in certain scenarios, if you have what are called centered variables, the property of being uncorrelated and the property of being orthogonal, which is just a fancy term for perpendicular, are actually identical conditions. So this is a very deep and fascinating connection. It's probably my favorite fact in math, or favorite perspective in math. But basically just remember, if two things are perpendicular, it's hopefully fairly intuitive that that might mean something like they're unrelated also. So what this means is Y and X are unrelated once we account for Z. And these vertical bars here mean given in statistics and math generally, so they mean given Z, or in other words, once we account for Z. So Y is independent of X once we account for Z, even though Y and X are related at the margin. Here, margin actually means something different. It means just not controlling for anything else. I know jargon is terrible. This is something that took me a very long time to learn, and now it's second nature, and I find myself saying these things and realizing I should clarify. And many people don't until they're asked, so I hope I'm not doing too bad of a job. But yeah, marginal association here means simply, rather than a little bit, it means associated without controlling for something else. Those are the two important meanings of marginal. So we'll see that this is actually true in our main running example, that we actually have a spurious relationship, and I'll show kind of a diagram of what that looks like, in that the number of siblings that you have, once you account for things that could plausibly cause both your number of siblings and your score on this vocabulary test, once you account for those things, it's really not clear that there is actually any relationship left over. So how could we infer causality from observational data? Well, it's difficult, but it can happen under certain circumstances. First, we need an empirical association. This is pretty easy. We can do this with numeric and graphical methods. They can be a little intimidating at first, but we'll learn them, and they're basically just math. There's not a lot of deep thinking in the formulae. I mean, there can be. Really understanding the formulae actually requires some deep thinking, but these are easy to compute when we're just trying to conduct a practical research project. Temporal priority is something else that we need. Basically what this means is that whatever else people agree or disagree on with respect to causality, usually we think that for X to cause Y, X must precede Y in time or precede it temporally. So this has to be in place. The problem is that we typically only have cross-sectional data, such as on the GSS or CPS. That means that we only observe people at one particular point in time. So for instance, if we're thinking about, say, someone's additional job training or some kind of further education that people pursue later in life, and that happened, say, prior to, or really actually only in the year of the GSS, for instance, it's hard to say whether that might cause someone to have a higher income or whether they might have pursued that because they have a higher income prior, if both of those things happened in the past. In general, when you only have cross-sectional data, you can find associations, but it's often not clear whether X causes Y or the reverse. We also need non-spuriousness. This also is kind of what I was saying before. By the way, this list comes from Chambliss and Shutt. What this means is that we have to make sure that we've properly modeled, which is surprisingly difficult, and people often don't give it enough thought. We need to make sure that we've properly modeled our scenario, or we've come up with a good model, basically. And then we want to make sure that we've measured and included in our estimate of the model parameters all of the relevant confounders. I'll say more about confounders later. Then ideally we need to identify the mechanism. So even still, we could have this problem of mutual determination where maybe X causes Y at some times, but then Y later causes X. And we need to understand on a qualitative level how all of this works in order to say very much. And finally, we typically need to specify the context because even still, usually it's not the case that X always causes Y. Hopefully, it's true for some population of interest that this is true in a specific time frame, but it's quite rare, really, to find scenarios where X always has the same effect for everyone. And that's maybe not as daunting as it seems because you might say, well, the level of education for every person doesn't always lead to a change in their income. And that's true, but that's because people differ on things besides income. Really, what we're saying here is it might be the case that even when every single person, for example, once you include all of the relevant covariates and all of the interactions, that even still it might be the case that for unknown reasons, people just differ on this variable, and that can be quite challenging as well. So you want to specify that context. So let's look at an example of reverse causality so you can see a little bit more in detail what I mean. So here's our running example. First, we're going to just lay out the most kind of intuitive form, but then I'll discuss some possible misleading situations. So here's a basic example of a relationship between two variables, as the two I mentioned before. On the y-axis, we've got the number of words correct on a 10-item vocabulary test, and on the x-axis, we've got the number of siblings. I omitted some very extreme outliers here. You can see some people have very high numbers of siblings, but there was an interesting gap between 17 and about 23. So even though 17 is an enormous number, the fact that there were no observations between 17 and 23 made me think that 23, you shouldn't drop outliers willy-nilly, but in those scenarios, it's often okay. In fact, I would say it's almost always okay to run the analysis without outliers and then simply point that out and include analysis with them back in. Anyways, what this shows us here, this is a line of best fit here. For now, you can just interpret this very simply. It's the line that minimizes the sum of squared residuals, which are basically sample estimates of the error. in the sample. So this line basically makes the cloud of points as close as possible in straight line distance terms from it. You can see that there's a little clustering here on the scatter plot. I added a jitter artificially, which means that these points actually would be all lined up at these exact integer values, because number of siblings is a discrete variable and number of words correct is also a discrete variable. So the scatter plot would look a little bit dotty otherwise. It still looks a little bit dotty, but what I did was add random noise in the places where more data are concentrated. So for instance, if I didn't do that, you would look to the reader that the number of observations at 10.0 is 1 dot and the number of observations at 3.6 is 1 dot, but in fact there's many more at 3.6. Okay, so this appears to show a negative relationship. The number of siblings that you have would, to the untrained eye, somehow cause you to have a lower vocabulary score, maybe because you are deprived, or maybe because you're distracted, or something like that. These aren't very plausible stories, but we'll see later on that it's easy to get mixed up in more complicated scenarios. So first of all, one thing I'll point out, even though it's not very plausible here that the number of words correct on this test would cause your number of siblings to decrease, this is still mathematically valid. So as we'll learn later, where r is the correlation coefficient between x and y is identical to the correlation coefficient between y and x. This is not actually a correlation coefficient, it's a regression slope, but it's fundamentally the same type of thing. What that means is that you can find an association between two variables, whether or not, and in some cases there is actually zero distinction between one of them being the predictor in reality and one of them being the outcome in reality. So in other words, if you have two variables, one's the predictor, one's the outcome, and you know this to be true for sure. So for instance, if you think about something like, your parents' age when you were born, and then your age when your first child is born, there's no way that your age when your first child is born can possibly cause your parents' age when you were born. It's physically impossible. But it would still be the case that if we predicted the age when your parents had you from your age when you have your first child, this actually would in fact show a mathematical relationship, and mathematically there's nothing wrong with it. So even in scenarios where it's not just wildly implausible but impossible, you can still do the same basic math and it's fine. So this is a difficulty that we encounter in empirical research. You might also see mutual causality. Here I'm showing that example from before where I plot the respondents' education on the x-axis and their spouses on the y. Again, when I'm not even distinguishing between husbands and wives, or, that's really the only scenario where there's even a difference, right? Because in the case of homosexual relationships, the gender is by definition going to be the same. There's other types of relationships out there too, but I'm just going to kind of stick to those three. So in general, it doesn't really make a lot of sense here to even say, does a person's education cause their spouse's level of education or vice versa, because we can hardly even distinguish who the person is and who the spouse is. So in general, and even if you think about husbands and wives, it's probably the case that they're mutually causal, right? Even though we can distinguish husbands and wives, husbands, I guess by definition, being men in the partnership and wives being women, it seems entirely plausible that this is mutually causal. So the data obviously cannot tell us which is which. We could swap the axes here and it would produce the same type of graph and there would be no difference. So the data cannot tell us which variable is the real causal variable. I just happen to put spouse on the y-axis because respondent is the person who actually answers the survey, and so I put them on the x just because that seems to be somewhat more intuitive graphically, but it really doesn't mean anything. Finally, you can also have the case of confounded causality. A confounder is a variable that causes both some alleged causal variable x and the outcome variable y. So here's an example of how that might work in our scenario. Again, remember that this means this is a case where x and y are confounded, meaning that y is actually independent of x once you account for z. So in this scenario, y is word sum, or the vocabulary score. X is siblings, the number of siblings, I'm just using the GSS variable names here, and Z is parents' education, which is actually two different variables in the GSS, but you could just take the mean of them, and that's how I'm thinking of it here. So the simple model would be that there's just an arrow from siblings to word sum, and that's all there is, right? That was our basic, when we did that scatter plot before, that was implicitly the model. But you could come up with a more complex, but I think also more intuitive model where your parents' level of education probably causes the number of siblings that you have. It probably also causes your level of education, which then can cause your vocabulary score, and your parents' education probably has some direct effect on your vocabulary score, because even if you don't have a large degree of formal education, you might hear words in your home, and that sort of a thing. So in this scenario, note that if we don't, like, if this is the true picture of reality, but we don't control for parents' education or respondents' education, this association here will actually be transmitted, in a sense, back towards some. So if we ignore this variable and that variable, we will see an empirical association between these two, or a marginal association between these two in our sample. But if we do properly control for parents' education and respondents' education, then we should see actually no effect of the number of siblings you have on this word sum variable if this is the true model, and your siblings, the number of them that you have doesn't really actually impede your ability to learn vocabulary. So we'll actually be able to take a brief look at which of these we think is more plausible using a little bit of higher level statistics, and this is one reason to pay attention to experiments, is it sort of helps inspire these statistical techniques. So what I did here is on the x-axis, I regressed the number of siblings that people have on a set of variables that could also cause the number of siblings that you have, which could be the education of your parents, and then also your respondents, which isn't going to plausibly cause the number of siblings that you have, but it's a relevant predictor otherwise. And then what I did after that is I took that variation in the number of siblings that was unrelated to these things. So it's sort of like stripped of those confounders. It's the variation in number of siblings on its own. And then I saw whether that had a relationship to vocabulary score. So we're sort of controlling away for these other variables. And then here, what you can see, this gray bar here, it's not really a bar, kind of band, is the confidence interval for all the possible slopes that we think are plausible, given a 95% level of confidence. And you can see that because you could draw a flat line through here and remain in that gray bar, I know that wasn't very flat, but something like this here, because you could remain in that gray bar, what that means then is that we can't really say from the sample that there's any relationship between these two things. So this would make it appear that once we control for those other variables, it's not the case that we've got any association left over, significant association between siblings and vocabulary score, and so we would say that this does not cause your vocabulary score. It's pretty close. It's right on the margin of statistical significance, but we don't need to worry about that here. The point is that this kind of obvious relationship from before becomes a much less clear relationship. I guess this is the better one. Becomes a much less clear relationship once we account for these other variables, which makes a lot of sense. We would think that it's more intuitive that this for sure causes this, this for sure causes this, this for sure causes this, and the sort of like social psychological claim for this causing this is much more dubious. So now let's think about where that kind of logic of controlling comes from and talk a little bit about the merits of experiments. So experiments let us avoid these problems rather simply. We can observe associations with experiments, we can infer the temporal order of events because we assign people to treatment and control, and then we look at the outcome after people have gotten the treatment or not. We can control for confounders because we just make sure that the relevant covariates are balanced in the treatment and control group. And then we can ideally even observe the mechanism. So the ideal case of this would be something simple. A colleague of mine, for instance, in the botany department does really interesting research where she looks at the impact of stress on plants, and she basically built this crazy robot that strokes plants, basically, and it turns out that plants really don't like being touched by people very much, at least this type of plant, so that's highly stressful to them. So basically she has this robot arm periodically stroke some of the plants, but another set of plants is left to their own devices, and otherwise the two plants are basically the same. And it turns out that this is relatively easy to do because plants are pretty simple. I mean, they're very complex and cool in a lot of ways, but you can basically give them identical environments more or less pretty easily, put the same number of caterpillars on them and this sort of a thing. So that's basically the picture you should have in your head. That's what all of this jargon means. In human experiments, it's more complicated, but we can still usually at least get groups that have some kind of balance overall. So, for instance, if I'm interested in, say, the effect of, let's say, like, what would be a good example here? Let's say some kind of medication that I think might help with cancer. So I might think that whether or not someone has previously had cancer is a relevant factor. Now, I obviously can't just give people cancer to make sure that they can go in the control group and then we can have someone like that in the treatment group as well. But if you're just looking at the difference in means, which is what we almost always do, then it turns out that all you need is for the mean incidence of cancer in the treatment and control to be the same. And then that's relatively easy. You don't have to give anyone cancer. You can just recruit adequate numbers of people into each arm so that 10% of people in each group have had cancer. So that's experiments. They're really nice, and this is kind of a setup here. So basically, we have our population, we take a sample, as we've learned before. These can typically be random samples as long as people, are willing to also then take a treatment or not. Then we randomize people, so we give some people treatment A or treatment B. Treatment B could be a placebo, and it often is. And then we examine the difference in outcomes, typically the mean difference. So these well-designed experiments are often known as randomized controlled trials because, as I described on the previous page, the two key elements that you want to know are the use of a control and randomization. So controlling is the way that we refer to the process of making sure we have balance on these covariates in the different arms of the study as they're known. So again, if we're thinking about, maybe let me just pick a different example for the sake of varying it up a little bit. If we're interested in the effects of say, hypnotherapy that helps people with, say, fear of flying on airplanes, we may want to make sure that things like someone's daily level of stress, their caffeine intake, if they have a history of drug abuse or anything that induces psychosis, prior exposure to planes. Basically, that's the type of thing that we would want to make sure is more or less balanced in each arm. This can get tricky because that list of covariates could get very long, so you want to think carefully about what you think would plausibly need to be controlled for and what you could kind of just ignore. If the variables have no effect on the outcome, then it does not matter if they differ. So, for instance, actually with the plant example, I was going to use the plant example, but there almost presumably everything could matter, again, because plants are just kind of sensitive to their environment. But we might think that, for instance, a variable such as, again, with humans, it's actually quite difficult too sometimes, but maybe we think about something like whether or not, I don't know, just a stupid example, whether or not someone is a Chicago Bears fan versus a Green Bay Packers fan in that airplane example. That is probably not something that we need to adjust for, like the levels of support for teams. And then randomization means that there's no deterministic logic to the assignment to treatment and control. So that means that one group gets the treatment, the other group gets the control, and it doesn't have anything to do with the, the level of their covariates, basically. So once we have control, then we can randomize. It's difficult to randomize without adequate control. Well-designed experiments are also usually double-blind where possible. What that means is that the person administering the treatment and those receiving it are unaware of who's getting it, so we have what are known as placebos, meaning that some people, and this is not always possible, believe themselves to be getting the medication. This might seem unethical, but until we know the medication has got good support for it being helpful, there's really no problem with it, especially because it could be harmful, so it's really actually not an ethical quandary in most cases. And also because of different effects in how, say, doctors might treat people whom they know to be getting an actual medication versus a dummy medication, we also typically want to blind those people. You'll notice that I'm using kind of medical language here. Taken outside of a medical setting, this becomes significantly harder. So we'll see some examples of that later in the lecture, actually. So one reason that we like to do this sort of thinking about experiments, we will have opportunity to discuss later on when we can do this in the social sciences, but I want to let you know that the more common form of social science results that you'll hear reported has this logic of experiments behind it, but it uses mathematical techniques of the sort that I used earlier to control for that set of variables. So we can simulate experiments through the use of multiple regression, although we don't have time to investigate it in this course. So when you see phrasings such as, in our analyses of job satisfaction, we control for several family and background attainment characteristics drawn from the Wisconsin Status Attainment Model, which is a very famous model developed in the Wisconsin department. Or I estimate the union differential for the blah, blah, blah. Basically, I estimate earnings on a union variable and a set of controls. Or studies find that significant health inequalities between black and white Americans remain when socioeconomic status is controlled. When people say things like that, they're not actually doing experiments, they're doing multiple regression, and they're doing statistical control. It turns out to be very similar to bivariate regression, which I'll explain in a moment. We will learn bivariate regression in this class. What that looks like is we basically just write a multiple regression model like this. We say that y is equal to some set of variables x1, x2, up to xk. K almost always means the number of columns, which are variables in your data set, plus some intercept, which is beta naught, and all of the variables are going to have coefficients on them, so beta 1 is the coefficient on x1, etc. And then we've got some error term for everyone, so some random noise. And the idea is that if we include all the relevant factors in the model, then what's left over is just random noise, so we call that an error term. These models are really the workhorse of applied social science, and they're inspired by that logic of experiments. So we can use them to control for variables such as race, class, gender, etc. That's pretty wild in a way. Like, it's very cool that we can use these nominal variables in quantitative analysis. The trick involves the use of dummy variables, which, by the way, is not pejorative. It doesn't mean stupid or anything. It just means a variable that's very simple. And it's simple because we basically turn nominal variables such as religion into a whole set of binary variables. They're also called Boolean or indicator variables, such as Catholic, Protestant, Jewish, Muslim, Hindu, Buddhist, etc. They're coded 0, 1, and then we can use them in regression. I'll say a little more about that later, but that won't be a huge part of the course. So let's now turn and talk a little bit about experiments in some more detail, because while I do want to highlight the connection to statistical methods, it's worth discussing them in their own right at some length. So in theory, this shouldn't be the case, but is there anything other than the treatment that could affect the outcome with an experiment? So are there threats to the internal validity or reliability, as we learn to call it, of an experiment? And it turns out that that is possible. So first, you could just mess up the experiment. You could have unbalanced treatment and control groups, so the groups aren't comparable. You could have selection bias. So it could simply be the case that some people get recruited into the study who have unusual levels of the outcome variable or the predictors, and it might be the case that you have randomization with control, but the whole group is unrepresented. Even more important, you might have differential attrition, so if people drop out of the study, this is effectively a form of non-response bias, and those people will tend to be systematically different from others in the group. You could have endogenous change, which is a very interesting idea. So the testing process itself could have some effects, or if it's a longitudinal study, subjects mature. And in general, there's this phenomenon of regression to the mean, which says that very atypical subjects tend to become more typical over time. It's actually for mathematical reasons. I'll mention some of those later. There's also what we might refer to simply as history, which is a pretty general way to put it, but what this means basically is you might have some external events. So, for instance, while a testing process is happening, it might be the case that there's a large political shift, and this changes how people respond to some, again, let's say a hypnotherapy treatment that has to do with, let's say, anti-bias training or something. There might be contamination, so sometimes subjects end up directly interacting, and this obviously messes with the results. And you might have treatment misidentification, so the Hawthorne effect, which I'll explain in a moment, or the placebo effect just identified. Finally, you can have instrument decay or measurement error. Basically, what this means is that over time, the measurement becomes corroded. This is common in physical settings. It's a little less common in sociological settings, but sometimes, for instance, the way that you measure things at the start of a study and at the end of a study is quite different. I read an interesting study recently about the effects of different types of intervention for people that are having problems with their gender identity. And I won't discuss the study in too much detail, but there was one really interesting point that someone made, which, and this is a rare instance of this that I can think of, where people that underwent some kind of gender transition were given one type of depression questionnaire at the start of the study based on their gender at that point, and then later on they were given a different questionnaire based on their gender identity at the conclusion of the study. And that actually is a case of there being some sort of instrument decay in the sense that they simply took different tests. It might have seemed reasonable to the researchers or respectful of the people's identity to give them the different test, but unfortunately what it meant was that because these questionnaires, if you ask, adolescent boys and girls what they might be depressed about, there need to be a number of questions about the effects of puberty, and those simply end up not being relevant to some people. So it's kind of complicated. But otherwise, it's kind of rare. So we also have the problem of external validity, which we've typically referred to simply as validity. So this basically means that the experiment might be rigorous and well controlled, but it only identifies effects that exist in a laboratory. So the treatment might not be realistic. Even if there's no contamination effect, is there one in reality, or is the treatment just too clinical? So for instance, going back to the hypnotherapy example, you might have people do an experiment at the Mayo Clinic where they've got the world's best hypnotherapist. They're in this really, controlled setting. All they have to do for a little while is work on themselves. They have people pushing them to go to therapy and to journal after. And in reality, that might simply be stuff that people aren't willing to do. Maybe they can schlep to hypnotherapy 3/4 of the time, but they're not doing any of the other sort of adjunct stuff. And that might mean that they're not really getting it in the real world the way they were getting it at the Mayo Clinic. Oftentimes, too, it's hard to generalize the finding to a larger population. This is basically just, two things. One, it can be the problem of selection bias, which is kind of both an internal and an external problem. But we could also just have poor sampling methods in a variety of other ways. Selection bias, I guess, generally covers most cases, but there are some others. Also, there's simply the problem of replicability or sampling error. So sometimes you just get weird results by chance. That's the nature of sampling error. And the fact that we're controlling, although that does help us, let's say, cut through some of the statistical noise by saying, well, we know that, this variable X is confounded by this variable Z, but we controlled for Z. But unfortunately, there's still just sampling error. And all we can do is basically hope that by modeling the outcome, we're going to kind of reduce some of that noise overall. But there's still some that comes from the sampling process. So let me mention a couple of concrete examples here in some more detail that I prepared. So a good example of a threat to validity, or in other words, the you could think about this as really causing both types of validity problems. So internal or reliability and external would be the Milgram experiment. So the Milgram experiment, people may or may not be familiar with this. It basically was one of several experiments that were done around this time period. I think it was the 60s and 70s, where people were told by experimenters to shock individuals, or the other one of these, there's the Zimbardo experiment or the Asch conformity experiment. I'm forgetting the details of the the Zimbardo experiment, but in one of them, individuals were basically told to shock other respondents, and the researchers allegedly proved that they were able to manipulate subjects into doing this just through their authority. The Asch conformity experiment is similar. It's not as violent, but basically the researchers are allegedly able to manipulate people into saying that two lines that are very clearly the same length are different, or vice versa, just through peer pressure. And it's a pretty shocking finding, because then what it seems to tell us is, like, fascism basically is not the product of a specific set of circumstances that could, in theory, be avoided, but that humans are basically just always and everywhere prone to fascism. So it's a pretty shocking finding. It turns out that this is really not that true. So in this particular case, you can read this if you want, the link is here. Matt Hollander, who's another UW PhD in sociology, found that a lot of participants basically half-heartedly believed that the experimenters were playing a trick on them in some sense, which is true. And so what that means is that the treatment actually wasn't the real treatment. If you think about the real treatment as being the subjects were forced to take direction from researchers that they thought of as being honest and sincere and being very serious, that wasn't the case because they thought that it was in some way fake. So that would be a good example. Here's another one. This is a mask study that was done in Denmark, and this is now a little bit old and out of date. I'm sure people are probably tired of talking about masks, but also even this headline news last year. I taught this study when I first read it, which was late 2020, so I've been teaching this a long time, but it's a good example. So this is a study that basically assigned people to wear masks in a treatment group in Denmark, and then assigned people not to wear masks in a control group, and then they tested people to see if those individuals had COVID after a certain period of time. There's a variety of different problems with this, but one problem, whether you agree or disagree with the mask mandates, which are for better or worse, and I would say fortunately just behind us now, but whether you agreed or disagreed, we would say that one problem with this is that the claim that mask advocates made was that masks worked by protecting other people from your germs, basically, not protecting you from germs. And whether or not you think that's a plausible hypothesis or that physics could work that way, it is important to be clear that this is simply not actually testing the claim that the researchers wanted to test, whether or not masks work in the way that they are advertised. Here's another example. This is Hawthorne effects. This is another mask study. So in this particular example, this was a better study. These researchers in Bangladesh basically assigned different villages to treatment and control. So they assigned entire villages to wear masks or not, and or to promote them, I should say. They didn't actually have the power to basically force people to wear them. So this is a little bit better of an idea because what they're doing is testing and seeing, do masks work at the community level, which is the actual claim that mask advocates make. So that's why it's better designed, but it's still kind of problematic, and they're problematic because of the non-blinded quality of this study. So because people can see whether or not individuals are wearing masks, that presumably also influences their behavior. And another problem too was that the groups that, so this happened in Bangladesh. Bangladesh is a very poor country, and one reason that it was done there is that it was relatively cost effective, at least as far as I understand, for researchers to pay people to participate. And so there's also kind of a set of unfortunate incentives where even if people weren't directly paid, they understood that their village's participation in the study was contingent on there being some kind of interesting and significant results. And no doubt the people in the study understood what the results should be, because the null hypothesis would be that masks work. And because there was a lot of voluntary participation in testing, what this means, and also because different symptoms can be reported or not reported if they're mild, what this means is that there might be some effects from knowing that they were being observed, which is what Hawthorne effects are. So these are all threats to validity. Some of them are threats to internal validity, some are threats to external validity. You could make a case in any actual example that usually one thing that affects one affects the other. Sometimes they're cleanly distinguishable. If you want to think about a simple example where they're cleanly distinguishable, you could say that something that is wholly, say, valid but unlikely to obtain in the real world might be that if you have people take a test, say, in an extremely low oxygen chamber that would never occur on Earth and maybe is at the limit of human survival, that might be a situation that it could be completely well controlled, some exercise regimen you give people in that scenario, but it's simply unlikely to ever apply in the real world. And then a scenario that might be completely realistic, like let's say a simple intervention, say just 15 minutes a day of stretching or something that presumably the way you do that in a doctor's office could be more or less replicated at home. You could then have a scenario where the researchers just really botch assignment to treatment and control, and that would be not very reliable or would have poor internal validity. Okay, so those are Hawthorne effects. Now let's turn and talk a little bit about field and audit studies. So we've been talking a lot about lab experiments, and they have some benefits that you can typically strongly control the experimental settings, but they have some downsides. So you typically have small, possibly biased samples, so you have to watch that problem. You also oftentimes have a lack of realism, so you tend to have weaker external validity, even if you can, in theory, have strong reliability or careful following of experimental procedures. You could also think about field experiments. What these are experiments with random assignment, but in a natural environment. So you, I'll explain in a moment because they're somewhat hard to describe in general, but there's some common examples. So what these do is take advantage of situations where individuals are naturally being evaluated. So it's something like a job advertisement or an apartment rental. And all you need to do is, because presumably when people let apartments or they advertise jobs, the variables that can affect their decision are pretty much contained in the interview and a resume. So it's pretty easy to control for those things, surprisingly. And because these take place in the real world, you can have stronger validity. But as we'll see in a little bit, it's still, even if it's relatively easy to control for covariates, so you make people's resumes look very similar, but then you vary one thing, such as the person's race, this can still sometimes be a little bit difficult because it's a real world scenario and people might be, for instance, suspicious of what you're up to. Okay, so that's field and audit studies. Sorry, my computer is doing a little freezing here. Sorry, folks, I'm not sure. Finally, yeah, this is going ahead. It's a little weird. Okay, so let's discuss audit studies. So audit studies are a specific type of field study. They're the only type that we're really going to spend much time on. And what these do is take advantage of these naturally occurring evaluation opportunities. So for instance, subjects like employers or landlords won't know that they're participating in an experiment. They do tend to have greater realism and external validity, but some of the limitations include the difficulty of actually matching the different testers. So for instance, making sure that, for instance, people's resumes look more or less the same. You can also have a limited sampling frame, so the people that, say, for instance, are willing to hire or lease an apartment to you may not be a representative sample of the entire population, and you can sometimes have these experimenter effects. So it could be the case that the experimenters coach different people differently when they, say, apply to different jobs and this sort of thing. I'm presuming that when you watch this, you've read the Diva Pager article, or that you'll read it sometime soon. But that said, even though you've seen that described before, I want to describe these audit studies in a little bit more detail. So the sadly departed, unfortunately, Dr. Pager passed away a few years ago. I was actually in a class teaching some of her results when someone popped into the room and said it. It was really kind of a very sad coincidence. She got her PhD here as well. She was a professor at Harvard, and she conducted probably, I would argue, maybe the most famous experiment in sociology. Sociology doesn't do a ton of experiments, so there's more famous psychology experiments, but maybe the most famous sociological experiment. And all she did was have similar volunteers show up in person to apply for jobs with near identical resumes in Milwaukee, only their race and criminal record varied. So you may have heard the statistic before that a white man, study was only done on men, with a criminal record is more likely to get a callback than a black man without a criminal record in job offers, and this is a finding from that study. So her representation of the experiment is shown above right here. So what's going on in this scenario? We should stop and take a second and think about this. So we effectively have two factors here, whether someone is got a criminal record, quote unquote. These people did show up in person to these job interviews, but they also had resumes. So when we say criminal record, we mean that the resume indicated it. And then you also had the different races of the individuals. Effectively, we end up with four factors here. So white and a criminal record, white no criminal record, black and a criminal record, black and no criminal record. And then she tests basically for the differences in these means. It's a well-controlled experiment because most of the other variables that employers could theoretically discriminate on are contained in the resume, and these are modified so as to be identical. The applicants were visually similar in most ways besides race. They're young college students that Dr. Pager recruited, probably from UW-Madison. I don't actually know. That's probably not something we're allowed to know. But basically, this is a well-controlled experiment. So this is the principal finding here, and it's worth taking a look at this, practicing your graph reading skills. So you can see here, you've got the effects of the criminal record and the black and white job applicants. So you can see here these black bars represent criminal record and the striped bars represent no criminal record. And you can see here that white men with a criminal record were more likely to be called back than black men without a criminal record, which is a pretty striking finding. And you can see the results here. It's got a little bit of technical jargon in here. There's a p-value included. We'll actually learn what those mean in a little bit. You can ignore this, by the way. That's a typo. I'm actually just going to fix that now. I made that last year and forgot to fix it. So it's a pretty striking finding. And it's quite fascinating. It's really not clear why this might be the case. There's several theories. One theory would be that it's simple personal prejudice or bias, so employers simply don't like black respondents. There's a related theory that more or less comes to the same thing, but it changes the story a little bit, where employers falsely believe that black respondents are less capable, and so it's not so much a matter of personal dislike, but it's a sort of economic decision. It's still based in a claim that's not correct, but it does appear to be the case that there's a some distinction there between how you might think about this. But either way, it's clear that there's an effect of race on the probability of being hired. So this is a really interesting finding. We're kind of working on our first exemplar here. So part of an exemplar that we haven't, I gave you the kind of fun takeaway. It's not really that fun. It's very interesting, even if it's a little bit depressing. The kind of background here, though, is more important. And so when you do an exemplar, you need to think about what kind of questions someone was asking and why they went about studying the problem in the way that they did. And here, you might ask, why do we bother with an experiment? Why don't we just use observational data? Here's what Dr. Pager said: it's difficult using survey data to rule out the possibility that unmeasured differences between those who are and are not convicted of crimes may drive the observed results. So this is actually a really interesting point, and you can see that she's got here a model of confounding as well. So it could be the case that these background conditions like alcohol and drug abuse, behavioral problems, and poor interpersonal skills both cause incarceration and then also cause these employment outcomes. This wouldn't have anything to do with the race question directly, but if we're thinking about looking within races, recall that within both races, having a criminal record made you significantly less likely to get called back. In the black case, about 3 times less likely. In the white case, exactly half as likely. Pretty big effects in both groups. So just focusing on that problem, you might be interested, well, is it the case that when we observe people who have these criminal records having higher rates of unemployment, is it that they are being discriminated against, or is it that they have some of these bad skills that cause them to, at some point, both be incarcerated and then also to have bad employment outcomes? And what this is showing us here is, well, when you have a scenario where we don't actually have those problems because, we're controlling away from them, we're basically making up these resumes that said the people went to a good college and did all this stuff. The employer might not believe it, so that's one kind of realism point. But otherwise, we are kind of controlling away for those things because we're saying within that set of people that, might be assumed by employers to have these problems, but also we're kind of trying to communicate through the resumes that they don't, then it appears that there's still an effect. So this is a way to get around confounding. So are there some key limitations on Dr. Pager's study? Again, the realism in treatment is something worth noting. And again, by the way, you want to mention these limitations in your exemplar project. So possibly the demeanor between the race-paired individuals. She only used 4 subjects. And so this raises the probability that one person or other in each pair might have been a very unusual character. I don't know. Again, there's really no way. Presumably she, this is back in 2003, so it would have been harder, but presumably she has some tapes of how people actually acted. But it is, somewhat mildly unnerving to think that, we have these really strong research findings that have appeared very often in the media since then, but it was really only based on the acting skills or lack thereof of 4 undergrad men. No offense to undergrad men, of whom I was once one, but these, may not have been people with professional training. Second, generalizability. So she just did this in Milwaukee. We may or may not believe that Milwaukee generalizes. There's also a problem of realism in treatment. So these were people responding to classified ads, and it's not clear that those are a random subset of jobs. There's also the Hawthorne effect. So she made this really interesting point. Several testers commented that they felt irrationally bad about themselves when presenting themselves as ex-offenders, so they may have acted a little mopier, a little less confident, and this may have resulted in them. This is kind of one other factor, right? So if you think about it, the only things that these employers had to go on were the resumes and then the way that people acted, and presumably the acting was controlled, but it may not have actually been well controlled. So let's think about, relevant to that last point, just another fun study. Again, not super fun because these things are kind of gloomy in their outlook, but kind of an interesting study that picked up on some of those problems. So this is, again, how we think when we think about exemplars. Why do people redo studies? Why do they change what they change? So there's a very famous study as well that's related that did away with the problem of behavior or demeanor entirely, by using birth certificates and pre-experiment tests, to identify personal names that to most U.S. respondents encoded racial information. So to put it bluntly, they basically randomly sampled people who were not part of the experiment directly, but they just tried to see, if people would say that a particular name was black or white in basically its origin. And they found a set of names that are widely held by most people in their sample to connote that someone with that name is white or that they are black. And then they sent out identical resumes to employers. This is a really well-controlled experiment because they did away with the problem of acting. And there is like one problem here that you might think about, which is some people argue that names that are perceived as distinctly black might also be names that are perceived as working class, and names that are perceived as distinctly white might be names that are distinctly perceived also as upper class. It's not really clear if that's the case or not, but setting that aside, it's a really interesting study. And what the researchers found was that the callback rates for different names was quite significant. So the way you would read this table, you can look at basically the entire sample, then you can look at Chicago, Boston, then you can look at women specifically, males specifically, and then a whole bunch of other things. And then you can look at the callback rates as well. So you can see that for white names, for instance, there was a ratio of about 1.5, and they had a p-value here of basically 0, which means that the probability of results, if this is a well-controlled experiment, the probability of these results happening just by chance is effectively 0, which is a very statistically strong finding. And you can see other such ratios here as well. So this was attenuated in some cases. So women in sales jobs, for instance, there was a significantly smaller advantage for white-sounding names, but it was quite large in some other cases as well. Appears that for women in administrative jobs and in the city of Boston, this happened to be pretty pronounced. So the result, people use information and names to discriminate. This is a pretty well-established finding, and these results are more plausible because they have been established through experiments where it's really not clear what other information people could be using here. Really, again, the only debate is this based on personal animus, or is it based on a sincere, although mistaken, theory that black respondents, for instance, would be less capable, and it's more of an economic decision? That would be the primary debate here. I did also want to mention sort of at the very end here what we can do when we can't assign people to treatment and control, which we can't always. This is a really interesting study. It's a very famous one. I remember reading about this in high school, actually. I think I just learned about it on the Wikipedia page or something and then read it. It didn't make much sense of it at the time. I'm not trying to brag, but I did give it a go. So these situations where we might want to, say, look at two groups that are more or less comparable, but for the presence of a treatment we care about, one thing we can do is exploit situations where groups that are otherwise really similar happen to have some kind of exogenous event happen that doesn't really have anything to do with the covariates or the other properties of the group. An even more kind of overt example than the one I'm about to describe is this. You can look and see what the effects of, say, having a lot of money are for individuals who acquire a lot of money without having to change anything about their personal characteristics, which would be lotteries. So if you think about the problem of, say, comparing, let's say something like the effects of becoming wealthier on people's mental acuity. So you might look and see, you might say something like, okay, well, we need longitudinal data so we can follow people over time. And we see, this subsection of a once poor immigrant group does well over the course of their lifetime, and this subsection does not do as well. And hey, that shows us the effects of wealth. And someone might fire back, well, maybe what that's doing is actually just showing you the effects of being, say, a highly literate person, for instance. I'm just thinking about scenarios in my own group, like the different routes that people of Irish American heritage have taken in the United States. There's some pronounced differences. So some people might say, okay, well, all that's really showing you is some subset of that group made positive changes in their lives, and that actually has a lot to do. Maybe they went to school and read books and all this stuff, and maybe that explains not only their wealth but their better outcomes. So a natural experiment that does away with that problem is to look at groups of, say, relatively poor off people, but then look at people that won the lottery, because those people did not actually have to do anything significantly different to suddenly receive what's called an income shock in economics. And so this is a way to use this is a classic case of a quasi-natural experiment. Okay, so here's the example I originally started referring to. This is a very famous paper that studies the role of the minimum wage in employment. Card and Kruger examined the impact of a change in the minimum wage in New Jersey, pictured here, in April 1992, incidentally the month I was born, which was not matched by an increase in the minimum wage in the adjoining state of Pennsylvania, pictured here. So they looked specifically at Camden and Philadelphia, which are kind of in this area here, and these are basically cities that are kind of split more or less by the state border, but they're otherwise pretty much the same. So, they're, the same kind of metropolitan area, or at least close. I guess I'm not that familiar. Some people, I don't even know, actually. They might be a little bit far away from each other. I really should have looked this up. I looked it up last year and forgot. But at any rate, they're in a very similar part of the country, right? They're within short driving distance, and the state boundary is kind of an artificial imposition. Another example might be something like the difference between, say, the northern suburbs of Chicago and Kenosha-Racine, or again, the place I'm from, Kansas City, which is literally split across two states, or the case of like New York, for instance, and Hoboken. That would be another example. All these examples. Or you could look at, different DC compared to the places that it's close to on the Maryland and Virginia borders. So what you do in all of these studies is you have parts of a city or adjoining cities that are very, very similar in most ways, but there are changes at the state level that may not really have anything to do with the differences in the cities. They might just be effects of statewide politics that cause changes. So what the authors were able to do here is say, okay, well, you could say fast food employment in New York is higher than it is in, like, as a share of the population, than it is in North Dakota. And North Dakota has a lower state minimum wage than New York, so that proves that the minimum wage does not reduce employment. And someone could point out that North Dakota and New York are different in very many ways, and there could be a lot of different causes. The benefit of looking at New York versus Hoboken, or let's just use this example, the benefit of looking at Philadelphia and Camden is that these cities are probably otherwise quite similar. And so then if we change one of them, we can try to estimate the effects. So it's not a true experiment because we're not doing any assignment of subjects to treatment and control. But what we are doing here is we're basically looking and seeing, we've got this kind of backup mechanism for a treatment assignment that's almost random. It's not really random exactly because, again, it probably has something to do, with the stable differences between New Jersey and Pennsylvania, but it may not have much to do with the differences between Camden and Philadelphia. And so since we're concerned with this here, from the perspective of those two cities, the sudden increase in the New Jersey minimum wage may not actually do very much to explain those differences. So the result was there was no apparent impact of the minimum wage increase on fast food employment. And you can see here the authors employ this kind of difference in difference strategy. So it could be the case, and it did appear to be the case. You can see here, let's look to April 92. So prior to this point, the employment, and this is just an index, so these are both indexed to different values. They're 92 value. So they had already diverged by, if we look here, basically, or they're kind of indexed to the same value here, pardon me. But they kind of already been different at different times, and we might assume for them to be different at different times in the future as well. So what we see here, in fact, is that there are these differences that we see later on, but some of these are trends that are basically going in the same way. And also, if we look at the smaller set of counties, the counties are basically, the Pennsylvania counties and the New Jersey counties are basically on the exact same trajectory here. So that's quasi-natural experiments. Finally, I want to address survey experiments. You can embed these in a survey, so this is kind of what people have started doing. The GSS does this already, but this has become much more common in the age of digital surveys. That question about welfare and the kind of like racialized versions of welfare versus aid to the poor, that's basically an experiment on the GSS. But in general, you can have people, and this is again much easier to do on the internet, read different versions of the same text or the same question and then respond in different ways. Sometimes they're called vignette experiments, which means that people read a vignette or a short story or a lead up and then they answer different questions. Increasingly, this is done, although this is really not a good thing because it's very unreliable, with people that fill out Mechanical Turk surveys or surveys where people basically are paid to participate in these surveys and do what are called micro gigs. It turns out a lot of people actually try to make a reasonable amount of money in this way by just taking surveys all day. That's obviously in the first place not a random subset of the population, so we got to be concerned about that. They do have some strengths. They're relatively low cost. They have stronger internal validity when designed properly, and they have better generalizability than lab experiments. But the problems are that they lack realism, and there's not actually much observation of actual behavior, and the effects are unknown. So there's some examples here of having people read different articles where one article describes immigration in terms that are a little more racialist than the other, and then there were some effects that were observed. So it appeared that these racial shift condition respondents got, had basically feeling thermometers that were lower rated for other groups. But there's some problems here with this, and it turns out basically that these groups are, may not be stable over time in their different feelings. Also, there are some problems in the presentation of these error bars, but I'll say a little bit more about that later. So anyways, that's causality, why we care about it, experiments, how they help us infer causality, what we can do when we can't do experiments, and some special types of experiments that are a little more common in sociology, such as field/audit experiments and quasi-natural experiments. Thanks for watching.